Picture this, a light so ancient, it has been traveling through the vast emptiness of space for over 13.8 billion years. This light, the oldest in the universe, holds secrets about where we came from, how everything began, and perhaps even where we're headed. It's not just light, it's a cosmic time capsule, a whisper from the very birth of the universe itself. And today, we're diving deep into this extraordinary phenomenon. In this video, we'll uncover 30 mind-blowing facts about the universe's oldest light, known as the cosmic microwave background. From its discovery to its role in shaping our understanding of the cosmos, each fact will take you one step closer to unraveling the mysteries of our existence. So, if you've ever wondered how we can peer back in time to the very dawn of the universe, or what this ancient light tells us about dark matter, dark energy, and the fate of everything we know, you're in the right place. Get ready to embark on a journey through space and time, where every fact is a piece of the puzzle that makes up the grand story of the cosmos. Let's begin. Now, let's dive into the first fact about the universe's oldest light. The cosmic microwave background, often called the CMB, is essentially the afterglow of the Big Bang. Imagine it as a faint, ancient echo of the universe's explosive birth, still lingering in the vast expanse of space. This light is the oldest we can observe, dating back to a time when the universe was just a hot, dense soup of particles and energy. It's like a snapshot of the cosmos in its infancy, frozen in time and stretched across the sky. The story of its discovery is just as fascinating. In 1965, two scientists, Arno Penzias and Robert Wilson, were working with a large radio antenna when they stumbled upon a mysterious, persistent noise. At first, they thought it was interference, maybe from pigeons nesting in their equipment. But after cleaning the antenna and ruling out every possible source, they realized they had found something extraordinary. That noise was the cosmic microwave background, the faint whisper of the Big Bang itself. This discovery was a game-changer for cosmology. It provided the first solid evidence for the Big Bang theory, confirming that the universe had a beginning. The CMB also gave scientists a way to study the early universe in incredible detail, offering clues about its composition, structure, and evolution. Without the CMB, our understanding of the cosmos would be far less complete. It's not just light, it's a window into the very origins of everything we know. Now, let's take a closer look at just how ancient this light truly is. The cosmic microwave background dates back to a time when the universe was only about 380,000 years old. To put that into perspective, this was long before stars, galaxies, or even the first atoms as we know them existed. The universe was still in its infancy, a hot, dense fog of particles and energy, and the CMB is essentially a snapshot of that moment, frozen in time. What's truly mind-blowing is that this light has been traveling through space for over 13.8 billion years to reach us. That's almost the entire age of the universe itself. Every time we observe the CMB, we're essentially looking back in time, catching a glimpse of the universe as it was just moments after its birth. It's like holding a photograph of the cosmos as a newborn, one that's been preserved across billions of years. This incredible journey also tells us something profound about the nature of the universe. The fact that we can still detect this light today, after such an unimaginable span of time, is a testament to the vastness and endurance of space itself. It's a reminder that the universe is not just a place of immense scale, but also one of incredible history, with stories written in light that have been traveling since the dawn of time. As we continue to study the CMB, we're not just learning about the universe's past, we're uncovering clues about its very origins and how it has evolved into the cosmos we see today. And with that, let's move forward to explore another fascinating aspect of this ancient light. Now, let's shift our focus to what the cosmic microwave background truly represents, a cosmic baby picture. Imagine holding a photograph of the universe when it was just a few 100,000 years old. That's exactly what the CMB is, a snapshot of the universe in its earliest stages, capturing the moment it transitioned from a hot, dense plasma to a transparent gas. Before this transition, the universe was so hot and dense that light couldn't travel freely. It was like a thick fog with photons constantly bouncing off charged particles. But around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. This allowed light to break free and travel across space for the first time. The CMB is that first light, a relic of the universe's infancy, preserved for over 13.8 billion years. What makes this baby picture so extraordinary is the wealth of information it holds. The tiny fluctuations in temperature and density we see in the CMB are like cosmic fingerprints, revealing the seeds of all the structures we see in the universe today: galaxies, stars, and even planets. These fluctuations are the result of quantum processes that occurred in the universe's earliest moments, amplified by the rapid expansion of space. By studying this ancient light, we're not just looking at a moment frozen in time, we're uncovering the blueprint of the universe. It's like finding a time capsule that tells us how everything began and how it evolved into the vast, intricate cosmos we inhabit today. And as we continue to decode this cosmic photograph, we're piecing together the story of our origins, one photon at a time. With this deeper understanding of the CMB as the universe's baby picture, let's move on to explore another remarkable aspect of this ancient light. Now, let's turn our attention to something that might surprise you: the temperature of the cosmic microwave background. This ancient light, which has traveled across the universe for over 13.8 billion years, is incredibly cold. In fact, it's just 2.7 Kelvin, which is about -270.45 degrees Celsius. To put that into perspective, that's only a few degrees above absolute zero, the coldest temperature possible in the universe. But here's the fascinating part: the CMB wasn't always this cold. When it first emerged, the universe was a blazing inferno filled with intense heat and energy. As the universe expanded, it stretched the wavelengths of this ancient light, causing it to cool over time. Think of it like blowing up a balloon. As the balloon gets bigger, the surface stretches and cools. Similarly, as the universe expanded, the CMB's temperature dropped, leaving us with the faint, cold glow we detect today. This cooling process is a direct result of the universe's expansion, and it's one of the key pieces of evidence supporting the Big Bang theory. By measuring the temperature of the CMB, scientists can trace the history of the universe's expansion and understand how it has evolved over billions of years. It's like having a cosmic thermometer that tells us not just how cold the universe is now, but how it has cooled over time. And while 2.7 Kelvin might seem unimaginably cold to us, it's a crucial piece of the puzzle in understanding the universe's past, present, and future. With this in mind, let's explore how this ancient light continues to reveal even more secrets about the cosmos. Now, let's shift our focus to one of the most remarkable features of the cosmic microwave background: its near-perfect uniformity. When scientists first mapped the CMB, they were struck by how evenly distributed its temperature appears across the entire sky. The temperature is almost identical everywhere, varying by just a tiny fraction of a degree. This uniformity is a testament to how smooth and homogeneous the early universe was, a state that's hard to imagine given the vast, complex structures we see today. But here's where it gets even more fascinating. Those minuscule temperature fluctuations, as small as they are, hold the key to understanding how the universe evolved. These tiny variations in temperature are like cosmic fingerprints, marking the places where matter was slightly denser or less dense than average. Over billions of years, gravity amplified these differences, pulling matter together in the denser regions and leaving the less dense areas more empty. These fluctuations are the seeds of all the structures we see in the universe today: galaxies, galaxy clusters, and even the vast cosmic web that connects them. Without these initial irregularities, the universe would have remained a featureless sea of particles, and we wouldn't exist to observe it. It's incredible to think that the galaxies we see today, including our own Milky Way, owe their existence to these tiny ripples in the ancient light of the CMB. By studying these fluctuations, scientists can piece together the story of how the universe grew from a nearly uniform state into the rich, diverse cosmos we see today. It's like uncovering the blueprint of the universe's evolution, written in the faint glow of its oldest light. And as we continue to explore, these tiny variations will reveal even more about the forces that shaped our cosmic home. With this in mind, let's move forward to uncover how these fluctuations were first detected and what they tell us about the universe's earliest moments. Now, let's dive into how scientists first uncovered these tiny temperature variations in the cosmic microwave background, a discovery that revolutionized our understanding of the early universe. In the early 1990s, the Cosmic Background Explorer, or COBE, became the first satellite to map these subtle fluctuations in the CMB with incredible precision. What it revealed was astonishing. The universe's oldest light wasn't perfectly uniform after all. Instead, it carried faint imprints of temperature differences as small as 1 part in 100,000. These variations, known as anisotropies, were the first direct evidence of the seeds of cosmic structure. Building on COBE groundbreaking work, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, took the measurements to an even higher level of detail. WMAP maps were so precise that they allowed scientists to see the universe as it was just 380,000 years after the Big Bang. These maps showed not only the temperature fluctuations, but also how they were distributed across the sky, providing a detailed picture of the early universe's structure. What these satellites revealed was a universe that was far from smooth on the smallest scales. Those tiny ripples in the CMB were the fingerprints of density variations in the early cosmos, regions where matter was slightly more or less concentrated. Over time, gravity amplified these differences, pulling matter together to form the first stars, galaxies, and eventually the vast cosmic web we see today. The discovery of these anisotropies was a major triumph for the Big Bang theory. It confirmed predictions made decades earlier, showing that the universe began in a hot, dense state and has been expanding and cooling ever since. The patterns in the CMB also provided critical clues about the composition of the universe, including the amounts of ordinary matter, dark matter, and dark energy. As we continue to study these ancient temperature variations, they offer us a window into the universe's infancy, helping us piece together the story of how everything we see today came to be. With this foundation, let's explore how the next generation of missions, like the Planck satellite, built on these discoveries to refine our understanding even further. Taking the baton from COBE and WMAP, the Planck satellite launched in 2009, marking a new era in our exploration of the cosmic microwave background. Designed with unprecedented sensitivity, Planck was able to measure the CMB with a level of detail that far surpassed its predecessors. Its mission was to capture the faintest whispers of the universe's oldest light, and it delivered in ways that transformed our understanding of the cosmos. What made Planck so remarkable was its ability to detect temperature variations in the CMB down to a few millionths of a degree. These ultra-precise measurements allowed scientists to create the most detailed map of the early universe ever produced. The map revealed not just the temperature fluctuations, but also the polarization of the CMB, offering new insights into the universe's first moments. One of Planck's most significant contributions was refining our knowledge of the universe's composition. It confirmed that ordinary matter, the stuff that makes up stars, planets, and us, accounts for just 5% of the universe's total mass energy. Dark matter, which doesn't emit light but exerts gravitational pull, makes up about 27%. The remaining 68% is dark energy, the mysterious force driving the accelerated expansion of the universe. These numbers, now considered the gold standard in cosmology, were made possible by Planck's meticulous observations. But Planck didn't stop there. It also provided critical evidence for the theory of cosmic inflation, the idea that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. By studying the patterns in the CMB, Planck found subtle imprints that matched predictions made by inflation models. This discovery strengthened the case for inflation and gave us a clearer picture of how the universe grew from a tiny, dense point to the vast expanse we see today. Perhaps most impressively, Planck's data allowed scientists to calculate the age of the universe with remarkable precision, 13.8 billion years, give or take a few million. It also helped refine the Hubble constant, the rate at which the universe is expanding, though this measurement has sparked some debate among astronomers, hinting at new mysteries to solve. Planck's legacy is one of precision and discovery. By pushing the boundaries of what we can observe, it has deepened our understanding of the universe's origins, composition, and evolution. And as we continue to analyze its data, new questions emerge, reminding us that the story of the cosmos is far from complete. With this foundation, let's turn our attention to how the CMB provides evidence for one of the universe's most elusive components, dark matter. Now, let's dive into one of the most intriguing mysteries of the cosmos, dark matter. The cosmic microwave background doesn't just tell us about the universe's oldest light. It also holds clues about this invisible substance that makes up roughly 27% of the universe's total mass energy. But what exactly is dark matter, and how does the CMB help us understand it? Dark matter is a type of matter that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, its presence is undeniable because of its gravitational effects. For example, galaxies rotate faster than they should if only visible matter were holding them together. This discrepancy led scientists to propose the existence of dark matter, and the CMB has become one of the most powerful tools for studying it. When we look at the CMB, we're seeing the universe as it was just 380,000 years after the Big Bang. At that time, the universe was filled with a hot, dense plasma of particles. As the universe expanded and cooled, these particles began to clump together under the influence of gravity. But here's the key: the way these clumps formed depended on the amount and distribution of dark matter. The CMB's temperature fluctuations, those tiny variations we've talked about, are like fingerprints of the early universe. They reveal how matter, both visible and dark, was distributed at that time. Dark matter's gravitational pull influenced the way ordinary matter moved, creating patterns in the CMB that scientists can analyze. These patterns match predictions made by models that include dark matter, providing strong evidence for its existence. One of the most compelling pieces of evidence comes from the way dark matter affects the CMB's large-scale structure. Because dark matter doesn't interact with light, it was able to clump together earlier than ordinary matter, forming a kind of cosmic scaffolding. This scaffolding guided the formation of galaxies and galaxy clusters, leaving its mark on the CMB. Without dark matter, the universe's structure as we see it today simply wouldn't make sense. The CMB also helps us measure the amount of dark matter in the universe. By analyzing the size and distribution of temperature fluctuations, scientists can calculate how much dark matter was present in the early universe. These measurements align with observations from other sources, like galaxy rotation curves and gravitational lensing, creating a consistent picture of a universe dominated by this mysterious substance. So, while dark matter remains invisible, its effects are written all over the cosmic microwave background. By studying this ancient light, we've not only confirmed the existence of dark matter, but also gained insights into its role in shaping the cosmos. And as we continue to explore the CMB, we may uncover even more secrets about this elusive component of the universe. Next, let's explore how the CMB sheds light on another cosmic mystery, dark energy. Now, let's turn our attention to another cosmic enigma, dark energy. While dark matter shapes the universe's structure, dark energy is the mysterious force responsible for the accelerated expansion of the cosmos. And just like dark matter, the cosmic microwave background plays a crucial role in helping us understand this invisible yet powerful component of the universe. Dark energy was first discovered in the late 1990s when astronomers observed that distant supernovae were fainter than expected. This suggested that the universe wasn't just expanding, it was expanding faster and faster over time. But what could be causing this acceleration? Enter dark energy, a force that makes up about 68% of the universe's total energy content. The CMB provides critical evidence for dark energy's existence. When we examine the CMB's temperature fluctuations, we're essentially looking at a map of the early universe's density variations. These fluctuations tell us not only about the distribution of matter but also about the geometry of the universe, and here's where dark energy comes into play. Einstein's theory of general relativity tells us that the universe's geometry is shaped by its energy content. A universe dominated by dark energy would have a specific curvature, and the CMB's measurements align perfectly with this prediction. The CMB shows that the universe is flat, meaning parallel lines will never meet, a result that only makes sense if dark energy is present. But the CMB doesn't just confirm dark energy's existence, it also helps us measure its properties. By analyzing the size and distribution of temperature fluctuations, scientists can determine how much dark energy was present in the early universe and how it has influenced cosmic expansion over billions of years. These measurements reveal that dark energy has been a constant force, driving the universe's accelerated expansion since its early stages. One of the most fascinating aspects of dark energy is its connection to the CMB's large-scale structure. Dark energy's repulsive effect counteracts gravity on cosmic scales, preventing matter from clumping together as much as it otherwise would. This leaves a distinct imprint on the CMB, which scientists can use to study dark energy's influence on the universe's evolution. The CMB also helps us explore the nature of dark energy itself. Is it a property of space itself, as Einstein's cosmological constant suggests, or is it something more dynamic, like a field that changes over time? While we don't yet have definitive answers, the CMB provides a wealth of data that helps us test these ideas and refine our understanding of this mysterious force. So, while dark energy remains one of the greatest mysteries in modern cosmology, the cosmic microwave background has become an indispensable tool for studying it. By decoding the patterns in this ancient light, we've not only confirmed dark energy's existence, but also gained valuable insights into its role in shaping the universe's destiny. Next, let's explore how the CMB's polarization reveals even more secrets about the cosmos. Now, let's shift our focus to another remarkable feature of the cosmic microwave background, its polarization. Just as sunlight reflecting off a lake creates patterns of light, the CMB carries a subtle polarization that holds clues about the universe's earliest moments. This polarization isn't just a random effect, it's a direct imprint of the universe's infancy, offering us a window into events that occurred just fractions of a second after the Big Bang. Polarization occurs when light waves vibrate in a specific direction. In the case of the CMB, this polarization was created when photons scattered off electrons in the early universe. As the universe cooled and expanded, these photons were finally able to travel freely, carrying with them a faint but detectable polarization pattern. These patterns are like cosmic fingerprints, revealing details about the universe's structure and the forces that shaped it. One of the most exciting discoveries tied to the CMB's polarization is its connection to cosmic inflation. This theory suggests that the universe underwent an incredibly rapid expansion in the first moments after the Big Bang, stretching far faster than the speed of light. During this period, quantum fluctuations were stretched to cosmic scales, creating the seeds for the large-scale structures we see today. The CMB's polarization patterns provide evidence for this dramatic expansion, as they match the predictions made by inflation theory. But that's not all. The CMB's polarization also helps us understand the universe's reionization era, a time when the first stars and galaxies formed and ionized the surrounding hydrogen gas. This process left its mark on the CMB's polarization, allowing scientists to study how the universe transitioned from darkness to light. By analyzing these polarization patterns, researchers can also probe the nature of gravity itself. For instance, the polarization can reveal whether gravitational waves, ripples in spacetime, were produced during cosmic inflation. Detecting these primordial gravitational waves would be a monumental discovery, providing direct evidence for inflation and offering insights into the universe's very first moments. The CMB's polarization is like a cosmic time capsule, preserving information about the universe's birth and evolution. It's a testament to how much we can learn from the faintest whispers of light, and it continues to guide us as we unravel the mysteries of the cosmos. Next, we'll dive deeper into the theory of cosmic inflation and how the CMB supports this groundbreaking idea. Now, let's take a closer look at one of the most fascinating ideas in modern cosmology: cosmic inflation. This theory proposes that in the first moments after the Big Bang, the universe underwent an extraordinary burst of expansion, growing exponentially faster than the speed of light. To put it simply, the universe went from being smaller than a single atom to something unimaginably vast in a fraction of a second. This rapid expansion didn't just stretch space, it also stretched the tiny quantum fluctuations present at that time, turning them into the seeds for all the cosmic structures we see today, from galaxies to galaxy clusters. The cosmic microwave background plays a crucial role in supporting this theory. Remember those tiny temperature fluctuations we talked about earlier? They're not just random, they match the predictions made by inflation theory almost perfectly. These fluctuations are like a snapshot of the universe's earliest moments, frozen in time and preserved in the CMB. But it's not just the temperature patterns that tell the story. The CMB's polarization, which we discussed earlier, also provides strong evidence for inflation. During this rapid expansion, gravitational waves, ripples in spacetime, would have been generated, leaving a distinct imprint on the CMB's polarization. In fact, the search for these primordial gravitational waves is one of the most exciting areas of research in cosmology. Detecting them would be like finding a direct signature of inflation, confirming that this dramatic event really did shape the universe as we know it. While we haven't definitively found these waves yet, the patterns in the CMB's polarization give us strong hints that they're out there, waiting to be discovered. Cosmic inflation also helps solve some of the biggest puzzles in cosmology, like the horizon problem. This is the question of why distant regions of the universe, which should never have been in contact with each other, have almost identical temperatures. Inflation explains this by suggesting that these regions were once close together before being rapidly stretched apart, allowing them to share the same conditions. The CMB is like a cosmic detective, helping us piece together the story of the universe's birth. Through its temperature fluctuations and polarization patterns, it provides compelling evidence for cosmic inflation, offering us a glimpse into the universe's most dramatic moments. Next, we'll explore how the CMB helps us measure the rate at which the universe is expanding, a key piece of the cosmic puzzle. Now, let's shift our focus to how the cosmic microwave background helps us measure one of the most important numbers in cosmology, the Hubble constant. This constant tells us how fast the universe is expanding, and it's a key piece of the puzzle in understanding the fate of our cosmos. The CMB provides a unique way to calculate this rate. By studying the tiny temperature fluctuations in the CMB, scientists can determine the universe's expansion speed at different points in its history. These fluctuations act like a cosmic ruler, allowing astronomers to measure distances on a grand scale. When combined with other observations, like the brightness of distant supernova, the CMB gives us a precise value for the Hubble constant. Interestingly, there's been a bit of a mystery surrounding this number. Measurements of the Hubble constant from the CMB don't always perfectly match those taken from nearby galaxies. This discrepancy has sparked a lot of debate among scientists. Some think it might hint at new physics, like unknown forms of dark energy or even modifications to our understanding of gravity. Others believe it could be due to subtle errors in our measurements. What's clear, though, is that the CMB remains one of the most powerful tools we have for studying the universe's expansion. By refining our measurements of the Hubble constant, we're not just learning about how fast the universe is growing, we're also uncovering clues about its composition, its history, and its ultimate destiny. As we continue to explore the CMB's secrets, we're getting closer to solving some of the biggest questions in cosmology. Next, we'll delve into how the CMB reveals the shape of the universe, another fascinating piece of the cosmic puzzle. Now, let's turn our attention to one of the most intriguing revelations from the cosmic microwave background, the shape of the universe. The CMB has given us a remarkable insight into this cosmic geometry, and it all comes down to a simple yet profound idea: our universe is flat. When we say the universe is flat, we're not talking about a two-dimensional pancake. Instead, it means that on the largest scales, the fabric of space-time follows the rules of Euclidean geometry, the same geometry you learned in school. In a flat universe, parallel lines will never meet, and the angles of a triangle add up to exactly 180 degrees. This might sound like a small detail, but it's actually a cornerstone of the Big Bang theory. The CMB provides the evidence for this flatness. By analyzing the temperature fluctuations in the CMB, scientists can measure the curvature of space-time. If the universe were curved like the surface of a sphere or a saddle, those fluctuations would appear distorted, but the CMB shows no such distortion. Instead, it aligns perfectly with the predictions of a flat universe. This flatness has profound implications. It tells us that the total density of the universe, the combined energy of all matter, and dark energy, is exactly balanced. This balance is a key prediction of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. Without inflation, it's nearly impossible to explain why the universe is so perfectly flat. But why does this matter? A flat universe shapes our understanding of its fate. In a flat universe, the expansion will continue forever, gradually slowing but never stopping. It's a universe that will grow colder and darker over trillions of years, but it's also one that fits beautifully with our current models of cosmology. As we piece together these clues from the CMB, we're not just learning about the shape of the universe, we're uncovering the blueprint of its creation. Next, we'll explore how the CMB might hold clues to an even more mind-bending idea, the multiverse. Now, let's venture into one of the most speculative and fascinating ideas in modern cosmology, the multiverse. The cosmic microwave background, or CMB, might just hold subtle hints that our universe is not alone, that it's part of a vast, possibly infinite collection of universes. This concept, known as the multiverse theory, is still highly speculative, but the CMB offers some intriguing clues that keep scientists exploring the idea. The multiverse theory suggests that our universe is just one bubble in a cosmic foam of countless other universes, each with its own unique physical laws and properties. But how does the CMB fit into this picture? One key piece of evidence comes from the patterns we see in the CMB's temperature fluctuations. Some scientists argue that certain anomalies in these patterns, like unusually large cold spots or asymmetries, could be the imprint of collisions between our universe and neighboring ones. These collisions, if they occurred, would leave faint but detectable traces in the CMB like cosmic fingerprints. Another connection lies in the theory of cosmic inflation, which we've touched on earlier. Inflation, the rapid expansion of the universe just after the Big Bang, not only explains the flatness of our universe but also provides a mechanism for the creation of multiple universes. According to some models, inflation doesn't stop everywhere at once. Instead, it continues in some regions, creating new universes in a never-ending process called eternal inflation. The CMB, as a relic of the early universe, could carry subtle signals of this process, offering a glimpse into the larger multiverse. Of course, the multiverse theory is still far from proven. It's a bold idea that pushes the boundaries of our understanding, and not all scientists agree on its validity. But the CMB remains one of the most powerful tools we have to explore these cosmic mysteries. By studying its patterns and anomalies, we're not just learning about our own universe, we're peering into the possibility of a much grander cosmic reality. As we continue to unravel the secrets of the CMB, we're left with a tantalizing question: could our universe be just one of many? Next, we'll dive into how the CMB connects to another fundamental aspect of our reality, quantum mechanics. Now, let's take a closer look at how the cosmic microwave background, or CMB, ties into one of the most mind-bending fields of science, quantum mechanics. At first glance, the vast, smooth expanse of the CMB might seem far removed from the tiny, unpredictable world of quantum particles. But in reality, the two are deeply connected. The CMB's temperature fluctuations, those tiny ripples we've talked about, are actually a direct result of quantum processes that took place in the earliest moments of the universe. Here's how it works. In the first fraction of a second after the Big Bang, the universe was incredibly small and dense, governed by the strange rules of quantum mechanics. During this time, tiny quantum fluctuations, random variations in energy, were happening everywhere. These fluctuations were like seeds, and as the universe expanded rapidly during cosmic inflation, they were stretched out to enormous scales. Over billions of years, these stretched-out quantum ripples became the foundation for the large-scale structure of the universe we see today: galaxies, galaxy clusters, and even the vast cosmic web. The CMB is like a snapshot of these quantum seeds frozen in time. When we look at the CMB's temperature variations, we're essentially seeing the imprint of those early quantum fluctuations. It's a remarkable thought. The same quantum mechanics that governs the behavior of particles in a lab today also shaped the entire cosmos billions of years ago. This connection shows that the universe's grandest structures, things like superclusters of galaxies, have their roots in the tiniest, most fundamental processes imaginable. What's even more fascinating is that this link between quantum mechanics and the CMB helps us understand how randomness at the smallest scales can lead to order on the largest scales. The quantum fluctuations were random, but their effects were amplified by cosmic inflation, creating a pattern that eventually led to the formation of stars, planets, and even us. It's a beautiful example of how the universe transforms chaos into structure over time. As we continue to study the CMB, we're not just uncovering the history of the universe, we're also gaining insights into the fundamental laws that govern reality itself. Next, we'll explore how the CMB marks a pivotal moment in cosmic history, the formation of the first atoms. Now, let's shift our focus to a pivotal moment in cosmic history, the formation of the first atoms, a milestone forever recorded in the cosmic microwave background. Around 380,000 years after the Big Bang, the universe underwent a dramatic transformation. Before this time, the cosmos was a seething, opaque soup of charged particles, protons, electrons, and photons constantly colliding and scattering light. But as the universe expanded and cooled, it reached a critical temperature where electrons could finally combine with protons to form neutral hydrogen atoms. This event, known as recombination, marked the moment when the universe became transparent, allowing light to travel freely for the first time. The CMB is the afterglow of this extraordinary event. It captures the moment when the universe transitioned from a foggy, light-scattering plasma to a clear, light-filled expanse. Think of it like a cosmic sunrise where the first rays of light broke through the darkness, illuminating the universe in a way it had never been before. This light, now stretched into microwaves by the expansion of the universe, is what we detect today as the CMB. What's truly remarkable is that the CMB not only tells us when this transition happened, but also reveals the conditions of the universe at that time. The temperature fluctuations we see in the CMB are essentially snapshots of the density variations in the early universe. These variations would later become the seeds for galaxies, stars, and planets. Without the formation of those first atoms, the universe would have remained a chaotic, light-trapped plasma, and structures like galaxies and even life might never have formed. This moment also marked the beginning of the universe's dark ages, a period when no stars or galaxies had yet formed, and the only light came from the fading glow of the CMB. It wasn't until hundreds of millions of years later that the first stars ignited, ending this cosmic dark age and lighting up the universe once again. The CMB, then, is more than just a relic of the Big Bang. It's a record of the universe's first steps toward becoming the structured, luminous cosmos we know today. Next, we'll explore how this ancient light has journeyed across the universe, interacting with galaxies and galaxy clusters along the way, leaving subtle imprints that tell even more of its story. Now, let's follow the journey of the cosmic microwave background as it travels through the vast expanse of the universe. After the universe became transparent during recombination, the CMB began its epic voyage, stretching across billions of light years. But this ancient light didn't travel through empty space. It encountered galaxies, galaxy clusters, and other cosmic structures along the way. These interactions left subtle but significant imprints on the CMB, like fingerprints on a cosmic canvas. As the CMB photons traveled through the universe, they occasionally passed through massive galaxy clusters. These clusters, filled with hot gas and dark matter, exerted a gravitational pull so strong that they bent the path of the light. This phenomenon, known as gravitational lensing, subtly distorts the CMB, creating tiny shifts in its temperature and polarization. By studying these distortions, scientists can map the distribution of matter in the universe, even the invisible dark matter that makes up a significant portion of its mass. But that's not all. The CMB also interacts with the hot gas within galaxy clusters through a process called the Sunyaev-Zeldovich effect. When CMB photons pass through this gas, they gain a small amount of energy, shifting their wavelength slightly. This effect creates a distinct signature in the CMB, allowing astronomers to detect galaxy clusters that might otherwise be hidden from view. It's like the CMB carries a record of every cosmic structure it has encountered, offering us a unique way to study the universe's large-scale architecture. What's truly fascinating is that these imprints aren't just random marks, they're clues. By analyzing how the CMB has been altered during its journey, scientists can piece together the history of the universe's expansion, the growth of cosmic structures, and even the properties of dark energy. The CMB, in a sense, becomes a cosmic detective, revealing secrets about the universe that we couldn't uncover any other way. This journey of the CMB isn't just a story about light traveling through space, it's a testament to how interconnected the universe is. Every galaxy, every cluster, every particle of matter has left its mark on this ancient light, creating a tapestry of information that helps us understand the cosmos on the grandest scales. Next, we'll dive deeper into one of the most intriguing effects that galaxy clusters have on the CMB, the Sunyaev-Zeldovich effect, and how it helps us uncover the hidden structures of the universe. Now, let's zoom in on one of the most fascinating ways the cosmic microwave background interacts with the universe's largest structures, the Sunyaev-Zeldovich effect. This phenomenon occurs when the CMB photons pass through the hot gas found in galaxy clusters. As these photons travel through the gas, they collide with the high-energy electrons within it. These collisions transfer a small amount of energy to the photons, causing their wavelengths to shift slightly. This shift creates a distinct distortion in the CMB's temperature, leaving a unique fingerprint that astronomers can detect. What makes the Sunyaev-Zeldovich effect so powerful is its ability to reveal galaxy clusters that might otherwise remain hidden. Unlike other methods that rely on visible light, this effect works because it's based on the interaction between the CMB and the hot gas in clusters. This means astronomers can use it to find clusters that are too faint or distant to be seen through traditional telescopes. It's like having a cosmic X-ray vision, allowing us to peer into the darkest corners of the universe and uncover structures we wouldn't know existed otherwise. But the Sunyaev-Zeldovich effect isn't just about finding galaxy clusters. It also helps us understand their properties. By measuring the distortions in the CMB, scientists can determine the temperature and density of the gas within these clusters. This information, in turn, gives us clues about how galaxy clusters form and evolve over time. It's a bit like using the CMB as a cosmic thermometer, measuring the heat of the universe's largest structures. What's even more remarkable is how this effect ties into our understanding of dark matter and dark energy. Since galaxy clusters are dominated by dark matter, studying their distribution and growth through the Sunyaev-Zeldovich effect provides indirect evidence for this mysterious substance. Additionally, by mapping the locations of these clusters across the universe, we can trace the influence of dark energy, the force driving the universe's accelerated expansion. In this way, the Sunyaev-Zeldovich effect isn't just a tool for studying galaxy clusters, it's a window into the fundamental forces shaping our cosmos. As we continue to explore the CMB's journey, it's clear that every interaction, every distortion tells a story. The Sunyaev-Zeldovich effect is just one chapter in this cosmic narrative, but it's a crucial one. By decoding these subtle imprints, we're not only uncovering the universe's hidden structures, but also piecing together the grand puzzle of how everything came to be. Next, we'll turn our attention to how the CMB has been used to test one of the most profound theories in physics, Einstein's theory of general relativity. Now, shifting our focus to another groundbreaking application of the cosmic microwave background, let's explore how it has become a vital tool for testing one of the most profound theories in physics, Einstein's theory of general relativity. This theory, which describes gravity as the curvature of spacetime caused by mass and energy, has been a cornerstone of modern physics for over a century. But how does the CMB help us confirm its predictions on the grandest scales of the universe? The answer lies in the way the CMB interacts with the large-scale structure of the cosmos. As the universe expanded, the tiny fluctuations in the CMB we discussed earlier grew into the vast web of galaxies and galaxy clusters we see today. These structures, shaped by gravity, create what's known as gravitational lensing, a phenomenon where massive objects bend the path of light traveling through space. The CMB, being the oldest light in the universe, carries subtle imprints of this lensing effect as it passes through these cosmic structures. By analyzing these distortions in the CMB, scientists can measure how gravity behaves on the largest scales. Remarkably, the results align perfectly with Einstein's predictions. For instance, the way galaxy clusters warp the CMB's light matches the curvature of spacetime described by general relativity. This confirmation isn't just a victory for Einstein's theory, it's a testament to the CMB's power as a cosmic laboratory, allowing us to test fundamental physics in ways that would be impossible on Earth. But the CMB doesn't just confirm what we already know, it also pushes the boundaries of our understanding. For example, some theories suggest that general relativity might need tweaking on cosmic scales to account for dark energy or other mysteries. The CMB provides a way to test these ideas, offering a precise measurement of how gravity operates across the universe. If any deviations from Einstein's predictions were found, they could hint at new physics waiting to be discovered. What's truly fascinating is how the CMB bridges the gap between the very small and the very large. The quantum fluctuations that seeded the CMB's temperature variations originated in the early universe, governed by the rules of quantum mechanics. Yet, as these fluctuations grew into galaxies and clusters, they became governed by general relativity. The CMB, in this sense, is a cosmic bridge connecting the quantum world to the vastness of spacetime. As we continue to study the CMB, it's clear that its role in testing general relativity is far from over. Future missions and more detailed maps of the CMB will allow us to probe even deeper into the nature of gravity and the universe itself. Next, we'll dive into how the CMB reveals another key feature of the early universe: Baryon acoustic oscillations, the cosmic sound waves that shape the distribution of galaxies. Now, let's turn our attention to one of the most fascinating features hidden within the cosmic microwave background: Baryon acoustic oscillations. These are essentially cosmic sound waves that rippled through the early universe, leaving a lasting imprint on the distribution of galaxies we observe today. But how did these oscillations come to be, and what do they tell us about the universe's infancy? To understand Baryon acoustic oscillations, we need to go back to a time when the universe was a hot, dense soup of particles and radiation. In this chaotic environment, pressure waves similar to sound waves propagated through the plasma. These waves were driven by the interplay between gravity, which pulled matter together, and radiation pressure, which pushed it apart. As the universe expanded and cooled, these oscillations froze in place, creating a kind of cosmic fingerprint. The CMB captures this moment in stunning detail. The tiny temperature fluctuations we see in the CMB are not random. They reflect the peaks and troughs of these ancient sound waves. The distance between these peaks, known as the acoustic scale, acts as a cosmic ruler. By measuring this scale, scientists can determine how the universe has expanded over billions of years, providing a crucial test for our models of cosmology. But the story doesn't end there. These oscillations didn't just leave their mark on the CMB, they also shaped the large-scale structure of the universe. As the universe continued to evolve, the regions where matter was denser corresponding to the peaks of the sound waves became the seeds for galaxies and galaxy clusters. This means that the distribution of galaxies we see today is a direct echo of those primordial sound waves. What's truly remarkable is how precise this cosmic ruler is. By comparing the acoustic scale in the CMB with the distribution of galaxies in the modern universe, scientists can measure the universe's expansion rate with incredible accuracy. This has helped confirm the existence of dark energy and refine our understanding of the universe's composition. Baryon acoustic oscillations also offer a unique window into the early universe's physics. For example, they provide insights into the behavior of dark matter, which doesn't interact with light but plays a crucial role in shaping these oscillations. By studying these patterns, we can learn more about the mysterious substance that makes up a significant portion of the universe's mass. As we continue to map the universe in greater detail, Baryon acoustic oscillations will remain a key tool for probing the cosmos. They not only connect us to the universe's earliest moments, but also help us unravel its ongoing evolution. Next, we'll explore how the CMB sheds light on another elusive component of the early universe: cosmic neutrinos. Now, let's shift our focus to another intriguing aspect of the cosmic microwave background: its connection to cosmic neutrinos. These nearly massless particles are among the most elusive inhabitants of the universe, yet they played a crucial role in shaping its early history. The CMB offers us a unique window into their existence and behavior, revealing clues about the universe's formative moments. Neutrinos are incredibly lightweight particles that interact so weakly with matter that they can pass through entire planets without being disturbed. In the early universe, they were produced in enormous quantities during the Big Bang, flooding the cosmos with their presence. As the universe expanded and cooled, these neutrinos decoupled from the rest of the matter and radiation, traveling freely through space. The CMB captures subtle imprints of these cosmic neutrinos. While they don't emit light themselves, their presence influenced the distribution of matter and radiation in the early universe. This influence left a faint but detectable signature in the CMB's temperature fluctuations. By analyzing these patterns, scientists can infer the properties of neutrinos, such as their abundance and how they contributed to the universe's overall energy density. One of the most fascinating discoveries from the CMB is that neutrinos make up a small but significant fraction of the universe's total energy content. While they are nearly massless, their sheer numbers mean they collectively exert a gravitational influence on the cosmos. This influence affects how structures like galaxies and galaxy clusters form, leaving a subtle but measurable impact on the CMB's anisotropies. The study of cosmic neutrinos through the CMB has also provided insights into their mass. While neutrinos were once thought to be completely massless, observations of the CMB have shown that they must have a tiny, non-zero mass. This discovery has profound implications for particle physics, challenging and refining our understanding of the fundamental building blocks of the universe. By connecting the dots between the CMB and cosmic neutrinos, scientists have unlocked a deeper understanding of the universe's early moments. These ghostly particles, though difficult to detect directly, have left their mark on the oldest light in the cosmos, offering us a glimpse into the conditions that shaped everything we see today. Next, we'll explore how the CMB holds clues about another pivotal era in cosmic history, the reionization of the universe. Now, let's turn our attention to a transformative period in cosmic history, the reionization era. This pivotal chapter, which occurred hundreds of millions of years after the Big Bang, marked the moment when the first stars and galaxies ignited, flooding the universe with light and fundamentally altering its structure. The cosmic microwave background, or CMB, holds vital clues about this era, offering us a glimpse into how the cosmos transitioned from darkness to light. After the universe cooled and the first atoms formed, it entered a period often referred to as the cosmic dark ages. During this time, the universe was filled with neutral hydrogen gas, and no stars or galaxies existed to illuminate the void. But as gravity began to pull matter together, the first stars and galaxies burst into existence, their intense radiation ionizing the surrounding hydrogen gas. This process, known as reionization, transformed the universe from a neutral state to one filled with charged particles, allowing light to travel freely once again. The CMB provides a unique record of this dramatic shift. As the first stars and galaxies emitted ultraviolet light, they ionized the hydrogen gas, creating bubbles of ionized material that gradually grew and merged. These bubbles left subtle imprints on the CMB, particularly in its polarization patterns. By studying these patterns, scientists can trace the timeline of reionization and understand how it unfolded across the cosmos. One of the key discoveries from the CMB is that reionization was not an instantaneous event but a gradual process that spanned hundreds of millions of years. The data suggests that the first stars likely formed around 200 million years after the Big Bang, with reionization completing by around 1 billion years. This timeline aligns with observations of distant galaxies, which show evidence of early star formation and ionized gas. The CMB also helps us understand the role of early galaxies in driving reionization. These galaxies, though small and faint by today's standards, were incredibly energetic, producing vast amounts of ultraviolet light that ionized the surrounding hydrogen. The CMB's polarization patterns reveal how these galaxies distributed their energy, shaping the large-scale structure of the universe we see today. By connecting the dots between the CMB and the reionization era, scientists have gained a deeper understanding of how the universe evolved from a dark, neutral state to the vibrant, ionized cosmos we inhabit today. This era not only shaped the distribution of matter and light, but also set the stage for the formation of the galaxies, stars, and planets that fill our night sky. Next, we'll explore how the CMB reveals the precise composition of the universe, shedding light on the balance between ordinary matter, and dark energy. Now, let's shift our focus to one of the most remarkable insights the cosmic microwave background has provided: the precise composition of the universe. The CMB is like a cosmic recipe book, detailing the exact ingredients that make up everything we see and don't see around us. Through meticulous analysis of the CMB's temperature fluctuations and polarization patterns, scientists have determined that the universe is made up of three key components: ordinary matter, and dark energy. Ordinary matter, the stuff we're most familiar with, planets, stars, galaxies, and even our own bodies, makes up just 5% of the universe. It's astonishing to think that everything we can observe and touch is such a small fraction of the cosmic whole. The remaining 95% is invisible to us, yet it shapes the universe in profound ways. Dark matter, which accounts for 27% of the universe, is a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but its presence is felt through its gravitational effects. Dark matter acts like a cosmic scaffold, holding galaxies together and influencing their motion. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. The largest component, making up a staggering 68% of the universe, is dark energy. This enigmatic force is responsible for the accelerated expansion of the universe. Unlike gravity, which pulls things together, dark energy pushes space itself apart, causing galaxies to move away from each other at ever-increasing speeds. The CMB has been instrumental in confirming the existence of dark energy, as its patterns align perfectly with the predictions of an expanding universe driven by this mysterious force. Together, these three components, ordinary matter, and dark energy, paint a complete picture of the universe's composition. The CMB's ability to reveal this balance is a testament to its power as a tool for understanding the cosmos. It's like having a cosmic scale that measures not just the visible, but the invisible forces shaping our reality. As we continue to study the CMB, we gain deeper insights into how these components interact and influence the universe's evolution. Next, we'll explore how the CMB addresses one of cosmology's most intriguing puzzles, the horizon problem, and what it tells us about the early universe. Now, let's turn our attention to one of the most puzzling mysteries in cosmology, the horizon problem. Imagine looking at the cosmic microwave background and noticing something strange. No matter which direction you look, the temperature of the CMB is almost exactly the same. This might not seem like a big deal at first, but when you consider the vast distances between these regions, it becomes a head-scratcher. How can parts of the universe that are billions of light-years apart have the same temperature if they've never been in contact with each other? This is the essence of the horizon problem. To put it simply, the horizon problem arises because, according to the standard Big Bang model, there hasn't been enough time since the universe began for heat or light to travel between these distant regions. Think of it like two people standing at opposite ends of a football field. If they've never met or exchanged information, how could they possibly be wearing the exact same outfit? It just doesn't make sense unless there's something we're missing. This is where the cosmic microwave background comes in. The CMB's near-perfect uniformity provides a crucial clue. Scientists believe that the solution to the horizon problem lies in a theory called cosmic inflation. According to this idea, in the tiniest fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion, stretching far faster than the speed of light. This expansion would have smoothed out any temperature differences, creating the uniform CMB we observe today. It's like blowing up a balloon. No matter where you start, the surface becomes smooth and even as it expands. The CMB's temperature patterns not only support the idea of cosmic inflation, but also help us understand how the early universe could have been so uniform. Without inflation, the horizon problem would remain a mystery. But thanks to the CMB, we have a compelling explanation for why the universe looks the way it does, even across unimaginable distances. As we continue to unravel the secrets of the CMB, we'll next explore how it connects to the creation of the universe's first light elements, shedding light on the origins of everything we see around us. Now, let's take a closer look at how the cosmic microwave background ties into one of the most fundamental processes in the universe, Big Bang nucleosynthesis. This is the moment when the first light elements were forged, setting the stage for everything that came after. The CMB doesn't just tell us about the temperature and structure of the early universe, it also provides critical evidence for how the building blocks of matter came to be. Big Bang nucleosynthesis occurred within the first few minutes after the Big Bang, when the universe was still incredibly hot and dense. During this brief window, protons and neutrons combined to form the simplest atomic nuclei: hydrogen, helium, and trace amounts of lithium. These elements became the raw materials for stars, galaxies, and eventually planets like Earth. But how do we know this actually happened? That's where the CMB comes in. The cosmic microwave background carries subtle fingerprints of this early chemical recipe. By analyzing the CMB, scientists can measure the abundance of these light elements with remarkable precision. For example, the CMB reveals that about 25% of the universe's ordinary matter is helium, a figure that aligns perfectly with predictions from Big Bang nucleosynthesis. If the universe hadn't gone through this process, the proportions of these elements would look very different today. What's even more fascinating is how the CMB helps us test the conditions of the early universe. The temperature and density of the universe during nucleosynthesis left a lasting imprint on the CMB's patterns. These patterns act like a cosmic time capsule, preserving the conditions of that era for us to study billions of years later. Without the CMB, we wouldn't have such a clear picture of how the first elements formed. As we piece together the story of the universe's origins, the CMB continues to be an invaluable tool. It not only confirms the theory of Big Bang nucleosynthesis, but also deepens our understanding of how the simplest elements laid the foundation for the complex cosmos we see today. Next, we'll explore how the CMB might hold clues to one of the most elusive phenomena in the universe, primordial gravitational waves. Now, let's turn our attention to one of the most exciting frontiers in cosmology, the search for primordial gravitational waves within the cosmic microwave background. These elusive ripples in space-time, if detected, could offer direct evidence for cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. Primordial gravitational waves are thought to have been generated during the inflationary period, when the universe expanded faster than the speed of light. These waves would have left a unique imprint on the CMB, specifically in its polarization patterns. Scientists are meticulously analyzing the CMB's polarization to look for a specific signature known as B-mode polarization, which would be a telltale sign of these ancient gravitational ripples. The detection of primordial gravitational waves would be a monumental breakthrough. It would not only confirm the theory of cosmic inflation, but also provide a glimpse into the universe's earliest moments, when it was just a fraction of a second old. Imagine being able to peer back to a time when the entire cosmos was smaller than an atom. This is the kind of insight these waves could offer. So far, the search has been challenging. While experiments like the BICEP and Planck collaborations have made significant strides, definitive evidence of primordial gravitational waves remains elusive. However, the hunt continues with increasingly sensitive instruments and innovative techniques. Future missions, such as the proposed LightBird satellite, aim to map the CMB's polarization with unprecedented precision, bringing us closer than ever to uncovering this cosmic secret. The implications of finding these waves would be profound. It would not only validate our understanding of the universe's birth, but also open new avenues for exploring the fundamental laws of physics. For now, the CMB remains our best hope for unlocking this mystery, serving as a cosmic detective that holds clues to the universe's most ancient whispers. Next, we'll delve into how the CMB helps scientists predict the ultimate fate of the universe. Shifting our gaze to the grand cosmic horizon, let's explore how the cosmic microwave background holds the key to understanding the ultimate fate of our universe. The CMB isn't just a relic of the past, it's a roadmap to the future, offering clues about whether the universe will continue expanding indefinitely or eventually collapse in a dramatic event known as the Big Crunch. The fate of the universe hinges on a delicate balance between the forces driving its expansion and the gravitational pull of all the matter within it. The CMB provides critical data about this balance by revealing the universe's density, composition, and rate of expansion. For instance, the precise measurements of the CMB's temperature fluctuations and polarization patterns allow scientists to calculate the amount of dark energy, the mysterious force accelerating the universe's expansion. If dark energy dominates, the universe will likely expand forever, growing colder and more diffuse until stars burn out and galaxies drift apart. This scenario is often called the Big Freeze. On the other hand, if the gravitational pull of matter, both visible and dark, were to overcome dark energy's influence, the universe could eventually stop expanding and begin contracting. This contraction would lead to a Big Crunch, where all matter collapses back into an incredibly dense state, potentially triggering another Big Bang and restarting the cosmic cycle. The CMB's data helps scientists weigh these possibilities by providing insights into the universe's total energy content and the strength of dark energy. Interestingly, the CMB also supports the idea that the universe is flat, meaning it will neither collapse nor expand at an accelerating rate indefinitely. Instead, it will continue to expand, but at a slowing pace, eventually reaching a state of equilibrium. This flatness is a key prediction of the Big Bang theory, and the CMB's near-perfect uniformity reinforces this view. While the CMB doesn't give us a definitive answer about the universe's ultimate fate, it provides the tools to refine our predictions. Future observations of the CMB, combined with studies of dark energy and the large-scale structure of the cosmos, will bring us closer to understanding whether we're headed for a big freeze, a big crunch, or something entirely unexpected. For now, the CMB remains our most powerful guide to the universe's destiny, offering a glimpse into the cosmic forces that will shape its future. Next, we'll explore how the CMB's properties align with the anthropic principle, shedding light on why the universe seems so finely tuned for life. Now, let's turn our attention to one of the most intriguing questions in cosmology. Why does the universe seem so perfectly suited for life? This is where the cosmic microwave background and the anthropic principle come into play. The anthropic principle suggests that the conditions of the universe are finely tuned to allow the existence of life, and the CMB provides compelling evidence to support this idea. The CMB's near-perfect uniformity and its tiny temperature fluctuations are not random. They reflect the precise conditions needed for galaxies, stars, and ultimately, life to form. For example, the density of matter in the early universe, as revealed by the CMB, had to be just right. If it were slightly higher, the universe would have collapsed back on itself long before life could emerge. If it were slightly lower, matter would have spread out too thinly, preventing the formation of galaxies and stars altogether. Moreover, the CMB's measurements of dark energy and the universe's expansion rate also align with the anthropic principle. The amount of dark energy is incredibly small compared to what theoretical physics predicts, yet it's exactly the right amount to allow the universe to expand at a rate that enables the formation of complex structures. If dark energy were even slightly stronger, the universe would have expanded too quickly for galaxies to form. If it were weaker, gravity would have dominated, leading to a premature collapse. These fine-tuned conditions aren't just coincidences, they're essential for the existence of life as we know it. The CMB's data reinforces the idea that the universe's fundamental constants and laws are set in a way that makes life possible. This doesn't necessarily mean the universe was designed for life, but it does raise profound questions about why these conditions exist in the first place. Some scientists argue that the anthropic principle could hint at a multiverse, a vast collection of universes, each with different physical constants. In this scenario, we happen to live in the one universe where the conditions are just right for life. While this idea is still speculative, the CMB's properties provide a fascinating foundation for exploring these possibilities. As we continue to study the CMB, we gain deeper insights into why our universe is the way it is, and whether its fine-tuning is a cosmic accident or a clue to something even more profound. Next, we'll delve into how the CMB has revolutionized modern cosmology, transforming it into a precision science that continues to unlock the secrets of the cosmos. Now, let's take a moment to appreciate just how much the cosmic microwave background has transformed our understanding of the cosmos. The CMB hasn't just given us a glimpse into the universe's infancy, it has fundamentally reshaped the field of cosmology itself. Before the discovery of the CMB, cosmology was more of a speculative science, relying heavily on theoretical models with limited observational evidence. But the CMB changed everything, turning cosmology into a precision science grounded in hard data. One of the most groundbreaking aspects of the CMB is its ability to provide a detailed map of the early universe. This map isn't just a static image, it's a treasure trove of information that has allowed scientists to test and refine their theories with unprecedented accuracy. For instance, the CMB's temperature fluctuations have confirmed predictions made by the Big Bang theory, solidifying it as the leading explanation for the universe's origins. These tiny variations in temperature have also helped us understand the distribution of matter in the early universe, revealing how small irregularities grew over billions of years to form the galaxies and galaxy clusters we see today. The CMB has also played a crucial role in measuring the universe's composition. By analyzing the CMB, scientists have determined that the universe is made up of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These precise measurements have not only deepened our understanding of the universe's structure, but have also opened up new avenues for research into the nature of dark matter and dark energy, two of the most mysterious components of the cosmos. Perhaps one of the most remarkable achievements enabled by the CMB is the ability to test the predictions of general relativity on cosmic scales. The CMB's data has confirmed that Einstein's theory holds true even in the vast, expansive reaches of the universe, providing further evidence for its validity. This has allowed cosmologists to use the CMB as a tool to explore other fundamental questions, such as the shape of the universe and the rate of its expansion. In essence, the CMB has given us a new lens through which to view the universe, one that has turned cosmology from a field of educated guesses into a rigorous, data-driven science. It has not only answered many of our questions, but has also raised new ones, driving the pursuit of knowledge forward. As we look to the future, the CMB will undoubtedly continue to play a central role in our quest to understand the cosmos, guiding us toward even greater discoveries. Next, we'll explore what lies ahead for CMB research and how upcoming missions aim to uncover even more cosmic secrets. As we look ahead, the future of cosmic microwave background research is brimming with exciting possibilities. New missions and cutting-edge technologies are on the horizon, promising to reveal even more about the universe's oldest light. one of the most anticipated projects is the next generation of space-based observatories designed to capture the CMB with unprecedented precision. These missions aim to measure the CMB's temperature and polarization with such accuracy that they could detect subtle signals from the earliest moments of the universe, including potential evidence of primordial gravitational waves. Such discoveries would not only deepen our understanding of cosmic inflation, but also provide a direct window into the universe's birth. Ground-based experiments are also pushing the boundaries of what we can learn from the CMB. Advanced telescopes equipped with highly sensitive detectors are being developed to observe the CMB from remote locations, such as the high-altitude deserts of Chile and Antarctica. These environments offer ideal conditions for minimizing interference from Earth's atmosphere, allowing scientists to study the CMB in greater detail than ever before. By combining data from space and ground-based observations, researchers hope to create a more comprehensive map of the CMB, shedding light on questions about dark energy, dark matter, and the universe's ultimate fate. Another exciting development is the integration of artificial intelligence and machine learning into CMB research. These technologies are being used to analyze vast amounts of data more efficiently, identifying patterns and anomalies that might otherwise go unnoticed. This approach could lead to groundbreaking discoveries, such as new insights into the nature of dark energy or the detection of previously unknown cosmic phenomena. As these tools become more sophisticated, they will play an increasingly important role in unlocking the secrets of the CMB. The future of CMB research isn't just about answering existing questions, it's about uncovering entirely new mysteries. As we refine our ability to study the universe's oldest light, we may stumble upon phenomena that challenge our current understanding of physics and cosmology. Each new discovery has the potential to reshape our view of the cosmos, reminding us that the universe is far more complex and fascinating than we ever imagined. With every step forward, the CMB continues to guide us toward a deeper understanding of the universe's origins, its structure, and its ultimate destiny. And as we embark on this journey of exploration, one thing is certain: the universe's oldest light still has many stories to tell. As we wrap up this journey through the universe's oldest light, it's clear that the cosmic microwave background is more than just a relic of the Big Bang. It's a treasure trove of cosmic secrets. From its discovery in 1965 to the groundbreaking maps created by satellites like Planck, the CMB has revolutionized our understanding of the universe. It has revealed the universe's age, its composition, and even the seeds of its largest structures. It has provided evidence for dark matter, dark energy, and cosmic inflation, while also challenging us to rethink the very nature of space and time. Each of these 30 facts has shown us how the CMB serves as a cosmic time capsule, preserving the story of the universe's birth and evolution. But the story doesn't end here. The CMB continues to inspire new questions and discoveries, pushing the boundaries of what we know about the cosmos. As we look to the future with advanced missions and technologies on the horizon, the CMB promises to reveal even more about the universe's origins and its ultimate fate. It reminds us that the universe is a place of endless wonder, filled with mysteries waiting to be uncovered. So, what will the next chapter of cosmic discovery hold? Will we find evidence of primordial gravitational waves or uncover clues about the multiverse? The answers lie in the faint whispers of the universe's oldest light, waiting for us to listen. If you're as fascinated by these cosmic mysteries as we are, don't stop here. Dive deeper into the wonders of the universe, explore the latest research, and keep asking the big questions. The cosmos is vast, and its secrets are waiting for you to discover them. Don't forget to like, subscribe, and hit the notification bell so you never miss a journey into the mysteries of space. Until next time, keep looking up. The universe has so much more to show us.